So hello everyone and welcome back. In this session I will show you how to run your first simulation in T-flows. So we're gonna use the laminar flow configuration, a very simple case. Probably you've heard about it before, or maybe you had some experience with the backward facing step. This is a benchmark. It's one of the most famous or common benchmarks to test CFD codes, because it deals with quite an aggressive pressure gradient after this step right here. So we'll see all of these details in a couple of minutes. But before we dive into it, I just want to make it as a disclaimer that this is a T-Flows crash course. Obviously, it's let's say we're scratching the surface. So I'm not gonna go so deep into the coding details of such a problem or into the source code of T-Flows. For relevance and time limitation, but you're more than welcome, and I would be very happy to assist you if you want to dive into the source code itself. But this case is very straightforward and very simple. You can run it on your own laptop after following this tutorial. So without further ado, let's go to the terminal and start to set up our simulation. Let's go right here. And let's say you're in a working directory, which is, I'm gonna go to mine here to show you from the beginning where this problem resides. So let's say you're in the root before even entering the T-Flows directory here. And when you list, you see T-Flows in front of you. You can go inside this folder. And when you access the folder, you have the root, as we said before, the binaries, documentation, sources, and tests. And if you remember from the last episode, we compiled the code already. Since we compiled the code, then we expect to have the executables or the binary files inside the binaries directory. So if we sort this, or if we list it, we'll find that indeed we have the executables of convert, divide, generate, and process. So that's good news. That means that we can start right away by going to tests, which is the directory that has all the test cases or the benchmarks of the code, and through which we will teach this course. So that's good news. That means that we can go to tests right away, which is the directory that carries all the test cases or the benchmark cases, and which also we will use for this course. You will find lots and lots of cases that you can train yourself, practice, and come back with questions if you have any. So if we go inside tests and list what's inside, we'll find all of these types of flows and configurations, turbulence models, blah, blah, blah. But we want to start simple, so we will go to a laminar case. So if you go inside the laminar directory, you will find also several cases, out of which we decided to use the backstep phase, or the backstep, which is the backward facing step. It's a very famous problem in CFD, as I mentioned. And we will get into, let's say, non-orthogonal mesh. I want to show you the non-orthogonal case. And then you have these files inside. So every test case has main files, or should have main files, to construct the mesh, or should have an external mesh, and it will have two main files, files inside each test case. The first one is the domain file, which is the name of the problem, followed by .dom, which is the domain file. And the second most important, or let's say that's the first most important, or both are on the same priority, because that's the control file. So without the control file, you can't start the case, because that's the input, the input to a process, to the numerical solver to start the simulation. It has all the numerical setup inside it of parameters and, let's say, physical parameters and everything. And that's the domain file to construct the grid. So let's go ahead and maybe discover what's inside the domain folder. If you open this one and you go all the way to the top, you'll find that this is a type of a rudimentary file that's inherited in T-flows, and that's just used to represent the domain in a preliminary way, just to construct a mesh in a canonical approach. Because as I said, meshes that are constructed in T-flows are very basic because they are used for academic reasons, and more sophisticated meshes can be exported from a third party or maybe another software, and can be imported then to T-flows and converted to the local format. But for simple geometries like this one, we can simply modify it and also design it here in T-flows, because it's just a simple a group of points that you define here, the 16 coordinates of this domain through 3 blocks, and then here you define the blocks, and within each block you define the number of points for each block. So this is basically 61 nodes in the x direction, 5 nodes in the y direction, and 21 nodes into the z direction, and so on. So 61 nodes here means basically that the resulting computational domain will have 60 cells into that direction, and so on. Here you have boundary conditions. The boundary conditions here are split into 7 because, for example, the wall has a bottom wall here, bottom wall 1, bottom wall 2, bottom wall 3, and they're all walls. And here you have top walls 1 and 2, because those are split as 2 faces, or let's say 2 patches. And you have inlet and outlet, and those, the back and front, are regarded as periodic boundary conditions in this problem. So after showing you this file, you don't have to modify anything in this file as long as you're running the case. But if you want to maybe have a finer mesh, or you want to play with the resolution a bit to see the impact of the mesh on the domain, then you can modify these guys, because this is the number of nodes per block. So I'm gonna go out of this file now to show you what the control file or the input file consists of. And as you remember, when you deal with the Vim text editor, you want to go out and you didn't make any modification in the file, then you put :q, which is quit. If you modified something and you want to save it before quitting, then you have to put WQ, which is write and quit. But now we didn't modify anything, and if, in case that you're skeptical that you changed something, but you're not very sure if you changed something or you did something by mistake, then you put Q and then this exclamation mark, meaning that it forces the text editor to quit without saving. So it's basically like in the GUI when it says close it without saving, and then you say yes because you're not very sure. So let's get out and jump into the control file, and I will explain the rest of the files in a second. But if we go into this guy, so basically if you have any other control files, this is just a template, but you use this control file that is prepared, or we made it ready for you, that you can use it as a baseline. So the control file is quite self-explanatory. If you start with from all the way top, then you have the problem name. Obviously that's the problem name without extension. If you have a heat transfer, you're let's say transporting the energy or the temperature, you have the energy equation on or off. Then the time step is the most important, obviously here, which is the delta T and the number of time steps. And then here you have other parameters like how the interval that you save the results. Save the results every 30 time steps or 300 or whatever. And the backup save interval, meaning that you will have a backup file every 300 time steps here in this case, after which that you can retrieve the solution. So it's like it's a backup file, and from the name it's a file that you can restart the simulation. And it's very important actually when you deal with turbulent flow regimes, as we will see in maybe 2 sessions, what is this file used for. It's very important actually in turbulent flow cases. But in, let's say here, it's not very significant because it's a laminar flow case, so you don't have you don't have something really to decontaminate, but we will talk about this one later. And here save results at boundaries. You can put as no or yes. If you want to put it as yes, then you can have these face or boundary files, BND files. That saves just the boundaries. It saves the results at the surface patches of the domain. If that's not so important for you, you can put no. If it is, then you can switch it on. And here profiler info is just a block of a report that tflows gives you at the end of each simulation that basically reports to you where did I spend the time. So the time, 50% of the time was spent in the Navier-Stokes solver, or some of it was spent in communication modules between processors or whatever. And you have the option here to use ratio, so it's as like a percentage basically, or in seconds. So you can just report it in either in percentage or in percentile or in seconds. And there's here the monitoring points. This is not maybe relevant for this case either, but those are points that you can, in more complicated cases like a turbulent flow regime, you want to have 2-point correlations, or you can maybe monitor some flow parameter for a boundary condition to relieve the flow at the outlet or some stuff like that. So you can add here monitoring points. These points can be used obviously, as the name implies, to monitor some parameter and maybe take a decision according to that value. And there, after that, in the third block, you have physical models, which contains obviously the physical parameters, the density, viscosity, and heat capacity. And you can have more. All the keywords I will show you in a second where to find them in case you forgot about something and you want to retrieve it, or you want to add some other keywords to constrain the solution. And then you have the turbulence model, which is not activated here in this case because it's a laminar flow. Here you have numerical parameters. I'm not going to dive into these, but these are parameters that govern how the Navier-Stokes, the discretized form of Navier-Stokes, is solved or computed. And then you have other linear solver settings and some tolerances for the pressure velocity coupling scheme, and also the number of iterations that you need per time step. And here we come to an interesting part, because in initial boundary conditions, you need to initiate or you need to initialize. So here actually we come into an interesting part, because the initial conditions for each solution, you have to start from somewhere. And if you initialize the domain by an arbitrary value that is very far from the final solution, then you take longer to iterate in order to arrive at this final solution, the correct solution. But if you start from somewhere and somewhat a closer solution to the final one, then you are more likely to finish the conversions into in a smaller time interval, obviously. And this potential initialization, as the name implies, it has a potential to approximate the final solution in a way. So it starts from a hyperbolic tangent or some parabolic velocity profile that gives the domain a shape, let's say according to that parabolic domain, as we will see now in a minute. And that is way better than if you see the solution with arbitrary values, or if you give a flat profile for the velocity. Because at the end of the day, if you have a wall-bounded flow and you advect the flow in the streamwise direction to this wall-bounded flow, then you're more likely to have something like a parabolic profile or some parabolic-like profile for the velocity between the walls. But so that's the benefit of having this initialization domain. And then we come to the boundary conditions. You specify for each boundary you need 3 main things. So the boundary condition, so as the name of the boundary condition, and then the type, which is a wall here, wall, top wall, and bottom wall. And then you need values. For the values, you specify here obviously zeros because this is no slip boundary condition. And for the fourth and fifth, the third and fourth boundary conditions are inlet and outlet, which is here, the inflow and outflow or convective boundary condition to let's say to prevent backflow or reverse flow at the outlet patch. So with that said, let's dive into the simulation. I hope that I said here enough about the control file, but always if you have questions you can come back to me and ask. But it's as I said, we're scratching the surface. There is so much to learn about the code, but the best way to start is to run these test cases, and then you will find everything is opening to you. So before I start here creating the mesh, I just wanted to say that I created some automation scripts. You can think of them in this way, which is this run case and clean case. So clean case from the name is that a script that cleans the directory and it resets it back to this shape, basically, because we just started, we don't have any old files. So whatever happens from now on, clean case will bring you to this initial position. But for run case, it has all the required tools, and it submits automatically the task or the job to your processor to run the case, and then even flushes the results to you. But we're not going to use these scripts for now. I just put them there in case that you get stuck or you feel that you're struggling with something. Then you can run this. You can run the case through these automation scripts, because there is no error through them. You can just submit them, and then it will run the case for you, and then it will give you the results in the end. But what I want to do now with you is to decouple or to dissect what these automation scripts have. So that said, we can start already by creating the mesh or generating the mesh. And for generating the mesh, we need generate. We need the program generate, and that is just a script here that submits the main keywords to generate the mesh. So if you open it, it's basically very simple. It has the problem name, and those are just some indices that if you run the mesh yourself, you will be asked about these indices, that you submit them, and it also asks you about these options. So it's very straightforward. But now we need just one thing. We need to link or to copy the executable files here. So we need to bring the binaries here in order to execute them onto this test case, right? I hope that makes sense so far. Now we're gonna make a soft link. So a soft symbolic link is done in this way, that you write ln, and that's linking. It's like making a shortcut, basically, without copying the file, and I will tell you later why am I doing this and not copying the binaries or the executables themselves. And then -s, all of these options, you can find them in the manual of the bash. S is for symbolic and I is for interactive. And then you go some steps back to find the binary file. And the binaries directory that contains everything, we will just take everything by putting this asterisk, and then we flush them here, right? And then if we list again, we will find, that we have all of these shortcuts now, the 4 shortcuts, and the readme even got a link from the binaries directory. What we need to do now is just to execute. So now it came to the now we came to the interesting part, which is we are gonna execute. So if we want to execute, you have to use this /generate. Then you're using now the software, or it's like you're clicking on the software by your mouse, and then you're submitting this generate script that I told you about, that we prepared also. It's ready for you. And then you click enter, then you'll find that the mesh is being generated very quickly. And now that's the box that I said tflows is always reporting for you where it spent the time that it spent, in terms of percentages or in terms of seconds, according to your wish. So you can also have some kind of a meaningful stats on what's happening in the code. After the mesh is generated, you have either the option to divide it or not, but in this case we don't have to divide it because it's a laminar flow. It's a very simple case, so we want to also experience the pleasure of running in serial. We can switch to a parallel run or a parallel mode in the next phase or in the next session, maybe when we deal with the turbulent flow case. But since we constructed the mesh already, we can also go ahead and have a look. So if you want to have a look on the mesh, you can open ParaView in this way, and by this and sign, you're just running ParaView in the background or something, so you don't have to mess up something. Or let's say if you click Control C, if you type Control C, then it kind of gets you out of ParaView if you don't put this and sign. So that's why we play it safe and put this and sign, and then ParaView opens within a second. And then if you click here on open, then you can load the files. And what files are we interested in? Well, we're interested also, let's say, I can show you basically the VTU file, that's the main file, with the problem name .vtu. This is always the mesh file or the main file of your problem, the constructed mesh basically. It opens in ParaView and it's written in binary format. Now, if you want to visualize the mesh, click OK and apply. Then you can see the domain. It's very simple. And if you click here on surface with edges, you can visualize the mesh. And that's why actually here, this, as you see, it's only for, as I told you in the domain file, you have 5 nodes in the Y direction, which means that you have 4 cells. And that's the backward facing step, that's the facing step. And the problem is called non-orthogonal because of this, because the mesh is not orthogonal here in this case. It's definitely orthogonal here on the right and on the very left. But you have also a case that is orthogonal here also. So it's just two types of meshes that are represented here in the code, so you can also test the mesh quality between 2 cases with the same problem setup. So yeah, that's the domain here. You can play with it to see, let's say, I'm not sure what type of parameters you have here. You have, for example, wall distance, that you can see already that the wall distance here is the maximum. If we remove this surface with edges, maybe to so a little bit, see it a little bit better, then you can see that the wall distance in the center is the maximum because you're measuring the distance to the wall from here is 0 and then it goes up, and then here is even more augmented because you have a bigger distance. So you can play around with this to study the domain a bit. And yeah, the other thing that I can show you here is that the phases. So you have this domain also that you can visualize, which has the phases only. If you need to see something quick and dirty without visualizing the whole domain, you can see this is just representing the phases. So if you basically have a cut here or a slice, then you don't see much actually, right? So you don't see much because it's just taking the shells or these surface patches only. But back here again, maybe here there's nothing yet to see because those are just here boundary conditions that represents that this is periodic boundary conditions, front and back. Those are all with one color are the walls. You can see also here that inlet and outlet with different colors, and that's the boundary condition representation here. So it's just another way to visualize your domain, but it's definitely much lighter and smaller than the mesh file. And here you have shadows that is good to visualize maybe if you have a periodic boundary condition. And what's good about this is that here you see one face only because the equivalent of this face, so you can see already that it's visualizing one patch, because the equivalent of this patch on the other side, so we have back and the front is, since it's a periodic boundary condition, it's implemented intentionally in this way. in the code to represent one domain because the other is copied from it. It's basically copying the values from this phase to the other one as it's a periodic boundary condition. So that's why it's called the shadow, because it's the shadow of this surface on the other side. So now that we visualize the mesh in ParaView, we can go back and run the problem. But before running the problem, let's check once again the control file. And the control file, it has time step 0.01. The results are saved every 30 seconds. So that's not too long, so we can wait a bit. But let's go ahead and run it. I was just making sure that 30 time steps, not 300 or something, that at least we can see the progression of the solution. In order to run the case, as we did with the generate, you can go ahead and click process.process. And if you want to follow up on the solution or dump the solution log, let's say, if you want to make a log and dump the solution log into a file, you can use this symbol here, bigger than, then you say log, or let's say out results, let's call it serial case. And I put the and sign again, so I can make the process run in the background, and I can always view what's happening when I want to. But in case that you don't have this and sign and you type Control-C, then you will close the solver, or you will quit the process. The solver will not be running anymore. So if we do that, the process should be working, and the solver should have been started. So if you tail this problem, meaning that you want to see the last 100 line here, the last 100 line, and you tail them, so you see what's inside this folder. So you can see the solution is progressing already, and it's creating files and saving. Look here, for example, in the last instance here, so when it arrived at the time step 30, it saved the VTU file, which has the results, the mesh and the results of 30 time steps. And for every time step, you have the residuals of U, V, and W, and the pressure and the continuity. To have the here on the right, the Peclet number and the maximum Courant number, or the CFL on the left. And you have the flux values and the drop in pressure in the bottom here. So that's the structure of the code. Every time you run the solver, you will find your advection or the transport equations on the top here, U, V, W. If you're solving for energy or turbulent schemes, then you will have the transport equations of K, epsilon, omega, stuff like that. You'll find all the residuals here, and then you can also post-process them and monitor them in ParaView or in Python later. But for this case, the solver is still running. Let's see where it, so it arrived at 150 now. So now there are two ways to cut the solution or to stop the solution. In order to stop T-flows, you can either say exit now, and if you remember from the last or maybe the second or third session, I taught you about some command line interface essentials, that one of them was touch, and touch is creating a dummy file that you can use to make a specific functionality. And in this case, we create a dummy file that's called exit now. And this exit now is used for T-flows to stop the solution. So exit now for T-flows is a flag that once T-flows goes through every time step and searches for a dummy file that's called exit now. If it finds it, then it stops the solution. That's basically the idea, simply. And if it doesn't find it, then it carries on. So that's happening every time step. And obviously, once it has it, once it finds it, then it can terminate the simulation. There's another one also that's save now, which saves the results without terminating the solver. But if you touch it, then it means that it just gives you the result of this time step, but it keeps carrying on with the simulation. And since we said exit now, then if you tail now again, you will realize that the solution has ended, and it gives you the usual report that I talked about here in percentage or in seconds. That's up to the setting in the control file. So here in the control file you have it in seconds. So profiler info. If you have it in percentage, then it gives you the report in percentages here. So now let's go and visualize the results. It's actually very nice that we have lots of them. So you can see the advection of the flow through the domain a bit. And maybe go to ParaView again. And then we load the VTU files. Here in this case we're running in serial, so we can load the VTU files. Let's start with 90 for example, and now let's visualize the velocity contours. So you can see already that the flow is advecting, and here it drops when it faces the step. Then you have this circulation zone here because the flow is all of a sudden expanded on this pressure here, high pressure gradient. So if you can see already this beautiful pressure eye right here, if you visualize it, you see that the flow kind of makes sense here. So there are many options you can use in ParaView. I cannot cover all of them, but as we walk through the course, I will show you some of the main features you can use. For example, here if you visualize two contours at the same time, you can kind of split the domain into upper and lower halves, and then you can render the same view again but with a different flow variable. And let's say if you like this view, for example, which is non-orthogonal to the screen or to the monitor, but if you want to save this camera, then you can save it with this button, and then you have it as a camera tool. But there are also thousands of macros and some setups that you can load in Python, and then you can use them as an automation script. But let's say if we want to use the same camera here in the top as in the bottom, or in the bottom as in the top, then you click as you hover here over this monitor or over this screen, and you click on camera tool, and then it gives you the same view. And then you can visualize the velocity field, which is now visualized already. You can play with the color bar here, and you can maybe choose a different palette. It can give you a different representation or a different dimension, let's say. And here I want to mention something, because if you notice, you can see kind of pixelized picture about the flow. And that's actually not an artifact. That's the correct way to visualize the flow, and also maybe instead of saying that's the correct way, it is the representation of the current mesh to the flow field. So it's not lying. It's telling you what every cell center has. So if you can see those patches here, for example, that are not very pleasant, but it's telling you the true information that the computational domain is giving us. So if you click on this surface with edges, for example, you can see already that this is our mesh. So the domain is not lying. If we have a finer mesh, then you have a better resolution, and then you can have a much better representation of the flow because you have more details, obviously. But nonetheless, if you want to have a smoother representation, but not the most accurate, but a smoother representation for a scientific paper or for a project, or something of let's say an interpolated picture of the flow that looks a bit smooth than this kinky way, then you should go ahead and use one of the filters, and this one is called cell data to point data. And what it does, it's simply that it takes the value from the cell center. Let's hover over one of these here, for example, and let's say one of these cells has the value of something. Let's say here you have a velocity magnitude of something, but we don't really have the value on these nodes. we have the value at the cell center only. We have the value at the cell center only, and that's what gives us this picture. And what this filter does is that it kind of gives you an interpolation, or it gives the domain another dimension by interpolating the cell center values to the nodes, to the corresponding or to the surrounding nodes. And that gives us a smoother picture because it's an interpolation method all over the domain. So as you can see now, if we apply this filter, then you click back again on pressure, and it gives you a much smoother image of the flow. Let's do the same thing again with the velocity field here. You can see already that it gives you a much smoother picture. So yeah, after visualizing this, there is only one last thing that I want to mention before we end this session, which is the fact that you can also save or visualize different time steps at the same time. So again, sorry, maybe I did that very quickly. So if you hover over all the VTU files, you can find that there is some kind of a small arrow next to it, small arrow. And then if you click on that one and click OK, it selects the whole list of time steps that it contains. So if you select this one, it loads already all the time steps that you've saved of solution in your directory. So if we have this here, let's say I'm going to use camera 2, and then here we want to visualize the velocity, and here we want to visualize the pressure, but maybe, yes, maybe here we don't have the filter, but no problem. And we want to click on play, but here maybe it gives you a bit of an ugly shape because the domain is not very the flow is not affected fully, and at the same time at the beginning you have a very rough initial value that kind of you have to clip it somehow. With these filters you can, or with these tools you can rescale the visible range of the data. But you get the point that if you start the domain from here, from point 0 or time step 0, you can with this button click play, and then you can see that the flow is being affected already. You can see it right here. But of course, if you run the simulation further, and then you have much more time steps till the flow, let's say, is fully developed or something, then you can have a more complete picture of this movie. And if you fancy saving this, then you can go ahead and click on save or file, and then save animations. And then let's say if you want to create a file for this, you can call it maybe animation, and then save this, test. If you save this, then it gives you the option, if you want to save all views, then you say, yes, I want to save all views because I have both of these contours together, pressure and velocity. Say save all views, and then you can also choose the resolution if you want to make it of a better resolution. But here we didn't use the filter, so it's not maybe the best picture anyways. But if you want to use the filter to make a very smooth image, there are also so many features and so many tools you can use to optimize your animation from ParaView here, and also maybe interact with other softwares like Blender. But as I said, this is only a crash course, so I want to give you as much as I can, but at the same time I don't want to overwhelm you with the information from CFD software to visualization tool to automation stuff. So I just want to give you a survival kit that you can have some nice images for your simulations, but then you can dig deeper later if you want. Then you have other tools here if you want to create a transparent background or a white background or whatever, and you click OK. Then it saves all the time steps. Here it's very quick because it's let's say a course domain and not so many time steps. And with these images you can create your video later, or let's say a GIF from a PNG, from a list of PNG files. Now I will show you how to use this to create a movie or to create an animation. So basically you can go to the directory where you saved the format, or you saved these pictures, and you can use a software package that's called Image Magic. but with CK, image magic, just like that. And once you install it, obviously using sudo apt get install image magic. In my case, I installed it already, so it's ready on my machine. So once you install it, you can use a tool that's called convert. So convert, and then you can specify the file name, and you put here an asterisk because you can see already we have test 0 time step 1, 2, 3, 4, 5, and these are the frames, not exactly the time steps, but the frames where we had solutions, or the layers of the solution we had in ParaView. Then you can convert the list of these files into a GIF automatically, which is a very handy tool. I find it pretty handy actually when visualizing the results or trying to discover what's happening inside the flow, the dynamics of the structures, of the flow. You can always visualize this through the convert kit, and you can here write maybe backward facing step.gif, and that will create for you a GIF format of these images that is very nice to visualize. You can basically use open or XDG open according to your system. Here let's try open, and then you can see already that you have a GIF, very nice, formed of these layers of pictures. So it's really very nice tool to use to create animations, and as I said before, if you use more filters or if you have a finer domain, then you can see more details through the flow field. Now one last thing I wanted to show you here is that these automation scripts, and these automation scripts that I created for you are very handy in case that you're stuck, or let's say you know already how the simulation is started and how the code works, but you need to kind of quicken up the process a bit, and you want to do other tasks. So in case that you already know what you're doing with the code, you can use these automation tools to make your lives a bit easier. So I want to show you first how to read them, what they contain before running them, and then we can run one of them. So basically, clean cases. To clean the case, you can see that it's a list of removals, removing these output files, the configuration dimensions, and PVTU, VTU files, and all of these. So we definitely want to run this script before we run the simulation, or if we need to get rid of some old files, not to have any contaminations. So the way to run it is to type sh and then clean case like this, and boom, you find that the case is all reset to the initial state. Here just we have the residual of this file, because backup was not included in the list of removals, but I will update that in the sources of the code. But you get the idea already that we got rid of all the other files and all the executables as well. So convert, divide, generate, and process are not there anymore. Once you have that, you're ready to start the new simulation, or you're ready to start the automation script that runs the simulation for you and also generates the mesh and everything. So here it's actually much simpler than it looks. It just here removes, it makes sure that these files are removed if you don't run the clean script before. Here it's kind of a security layer that it runs them anyways for you before it links, and this is the linking to the binary files, the executables. We did this step before. And then you have generate to generate the mesh through the generate script.scr that passes all the arguments to the generate executable. And then it asks you, please specify the run mode for me, either that you choose serial or parallel. And then it's read through this run, and if you say serial, then it runs the code in serial form, and if you say parallel, then it divides the domain into a specific number of subdomains that you pre-specify, and then you say this number of CPUs will run the processor, let's say 4 or 5 or 6, according to your requirements or your capacity on your laptop, and then you dump the results into these output results, parallel mode or serial mode in this case, and then you tail the results to see the output. If you enter anything else, then it will give you this error, obviously, because it needs you to pass one of these keywords, serial or parallel. So let's test that if it works. So it's I hope that it works smoothly, because you always generate something, develop it, whether it's simple or complicated, you implement it and it works on your side, but when you show it to someone else, then it's always embarrassing, huh? So if you run case, we saw already, we can, oh yeah, I was on the right way to run the case through sh. So it's a shell script or a bash script that you want to execute now, and if you click enter, then it starts already now by generating the mesh. So that's just generate smaller than, or you pass the generate.scr to generate executable, and then after it finishes, you will realize that it asks you a question. So it's waiting here on the user to input something. It asks you if you want to run in serial mode or in parallel mode. So let's run in serial first. Serial. Make sure that you type the word here, because it doesn't auto-complete it for you. So you have to write the whole word yourself. Then if you click serial, then you can see already that it quickly flushed it, but it says running tflows in serial mode, and then it starts to flush the output files or the output log that we saw before. And you can see that the solution is advancing here real time, and it's tailing the last 100 lines or so for you on the screen. So in case, let's say that the solution is running and you want to save it between two time step intervals, let's say, so here if you open a new tab by Ctrl+Shift+T, you open a new tab, and then you want to see what's inside the control file. So yes, we save the results every 30 time steps, but let's say we want to save the solution for some reason between 30 and 60, for example, at the time step 50 or 110 or something like that. So what we do is, let's say if we tail here, we are at time step 80. So before it gets to 90, we say touch save now, and that saves the solution. You can see already, it saved exactly on the 90, I guess. Maybe it saved on the 90. Let's see. Because yeah, but it's 90 is saving there anyways. Exactly, so it coincided with 90, but 90 is saved anyways, because that's how it's introduced in the control file. But now here we can say again touch save now, because we're after 120. So if you want to tail it, and then you can see already that we saved at 126, so it's locally, but just because the solution is progressing very fast, we couldn't see where it's saved. But if you want to see that, you can go to the output file, and then maybe let's go to the end of the file, go a bit back, and if you want to see, here is the time step that I clicked, or that I typed save now, and it was 126, even though that it was not pre-specified in the control file, but still saved the solution here and kept going with the simulation. So that's what save now does. And what obviously exit now does from the name is that it terminates the simulation. It closes the simulation. I guess that's a wrap for this session. It's quite some information to digest, and maybe it's good for you to practice this yourself, hands-on on your system, and figure out what type of issues that you might run through, or if it goes smoothly, then you might maybe need to navigate more through these control files and see for yourself what's the functionality of each object and each parameter, what it does, and the effect on the simulation. So you can play a bit and try to familiarize yourself with the environment, because the more comfortable you are with this working environment and the tests directory, the more confident you will become with the code. So yeah, that's it for this simulation and for this module, and I hope that it was simple enough and easy to understand for you. If you have any questions, don't hesitate to drop me an email that I will put in the slides, and it's always linked to the archive of this file. And with this, you should have hands-on experience, so you always make sure that you practice exercise by exercise and case by case. You have to sit by yourself and do it alone. And if you have any issue, you go back to the slides, or maybe send me that you have to make it yourself in order to understand and get the full experience of this course to benefit the most. With that, I guess that's all what I wanted to cover for this module. Thank you very much for watching, and see you next time. Bye.